Alright students, today we're going to talk a little bit about curvature, at least the first part of my lecture on curvature. A lot of times we've been talking about these vector valued functions, and we're going to eventually get to them as describing position as a function of time. But they describe out this path, and a lot of times it's convenient to think of that as you travel along some path out there, and you've got your position as a function of time. That t is time, and it tells you kind of where you are at any given time. So at 2 seconds you're at here, or at 3 seconds, ooh, that's kind of fancy. At 3 seconds you're at that point, at 2 seconds you're at that point, 5 seconds you're at that point. But curvature we're trying to look at as a feature of this path itself. It's saying like how sharp is that path. And the way that we typically define curvature is we look at it as the rate of change in the magnitude of the unit tangent vector with an arc length parameterization. So we're going to define t as the magnitude, there it is, of dt ds, where t is a function of s. And we've been talking about this a little bit, that t of t is your unit tangent vector. Typically as a function of time. Is usually how we start with it, because it's easy to find that in terms of time if our parameterization is in terms of time. But what we looked at, I think we looked at yesterday, was a parameterization of your unit tangent vector in terms of arc length. So you've got a particular path that you're following, and you can talk about your position as a function of time, but you can also talk about your position as a function of how much how much distance you've traveled. So you might be, this is where you are after you've gone 2 meters, here you are after 3 meters, here you're after 4 meters, you might be over here after 8 meters, and you're looking at your position on that curve as a function of the arc length, and we're looking at that in terms of how far you've traveled instead of what time it is. And I think we did that in a video yesterday. I think we got to that in class, but I'm making this video ahead of time, so I might have to do another video to fill in that little missing piece in there. But you're looking at your position as a function of time, and t of s is your unit tangent vector. And your curvature, we do it in terms of the position. We don't want it in terms of speed, because I think you've all experienced driving being on a car or on a bicycle or something, and the faster you go, it's going to affect the forces that you feel as you go around a curve. But we want this curvature to be a property of the curve itself, a property of the road. It's not something that changes depending on the time, on how fast you're moving, your time or your speed. We want it as depends upon your just as a physical feature of that curve. And so we've done it, if you do it in terms of arc length, then you're looking more at the physical feature instead of how fast you're going. So the curvature is defined again to be the magnitude of the derivative of this unit tangent vector in terms of your arc length that you've done. I think we may have seen that it's kind of a challenge to get your vector in terms of arc length. So a lot of times it's a lot easier to look at things in terms of time, because that's usually how our function is defined. So in terms of calculating the curvature, it's a lot easier to look at curvature as, well, I know that dt, or the rate of change in t with respect to big T, the unit tangent vector with respect to time, is well, yeah, it's I can do dt ds times ds dt, right? That's what we're looking for, that the rate of change in the unit tangent vector with respect to s. So this is the piece I'm looking for right here, the dt ds. But if I solve for that, I'll get that ds dt ds is equal to dt dt, the rate of change with respect to time, divided by ds dt. All right, but ds dt, that's the rate of change in your arc length with respect to time. That's just your speed, and that would just be the magnitude of r prime of t. And so that's the typical way that we'll look at calculating that, but it's one of the ways that you can calculate arc length. It still isn't the easiest way to calculate the arc length, but it works for finding the curvature, or finding the curvature is to take the rate of change in the unit tangent vector with respect to time and divide it by r prime of t, the magnitude of r prime of t. And these are both magnitudes. I've been using the double lines for magnitudes in class a lot. The textbook uses single lines, and I'm getting a little bit lazy in this section using the single lines too. People do both, so you got to be aware of both of those. So let's find the curvature. Let's take a pretty simple one. Let's take r of t, this vector function, and let's define it to be a sine t. Well, actually, let's do a cosine t. A cosine t, a sine t. So this is just a nice two-dimensional sort of shape. And what shape is that? Well, we saw that sine cosine pair, we just generated a circle. So this is a circle, and the radius is actually a. So it's a circle of radius a. But to find the curvature of a circle, I want to look at the magnitude of dt dA. So I need to find that dt dA. So that's the unit tangent vector. I need to find the unit tangent vector. And to find a tangent vector, we can start with the derivative. The derivative of a cosine t, derivative of cosine is sine, so that's going to be minus a sine of t. And the derivative of sine is cosine, so that would be a cosine of t is our tangent vector. And then the other thing I need is the magnitude of that. What's the magnitude of r prime of t? Well, that'll be the square root of minus a sine of t squared plus a cosine of t quantity squared, which would be the square root of a squared sine squared t plus a squared cosine squared t. And you can factor out the cosine. Oh, look, there it is. We can factor out the a squared, and we'll get a squared times sine squared t plus cosine squared t, all underneath the square root. But yeah, I lost the negative sign because I squared it. And that just simplifies down to a. So my unit tangent vector would be the derivative divided by its magnitude. It's going to be minus a sine t, a cosine t, divided by, so it's r prime divided by the magnitude of r prime divided by a. So it's just minus sine t cosine t. Alright, but to find the curvature now, I need to take a derivative again. I want to look at the derivative of t prime of t. I want to look at the derivative of the unit tangent vector. Well, derivative of sine is cosine, so I'm going to get minus cosine of t, and derivative of cosine is minus sine, so minus sine of t. So that is our t prime of t, that's the derivative with respect to t. So the curvature would be the magnitude of that one, t prime of t, divided by the magnitude of r prime of t. And we found the magnitude of r prime of t earlier. It's right up here, it's a. And then the magnitude of t prime of t, well, that will be the square root of minus cosine of t squared plus minus sine of t quantity squared, which is just the Pythagorean identity, which simplifies down to 1. So we end up with 1 over a as the curvature. It's a constant, does not depend upon t, and that shouldn't be too surprising if we're talking about a circle. A circle would have a constant curvature going on with it. And it's also 1 over the radius. The derivative is 1 over the radius, and so, or 1 over the radius of that circle. So that would be the curvature. Curvature as a quantity, if you've got something that's got a really slow curve to it here, your curvature is going to be small. So it's got a really small curve in this part of the graph through here. You've got a very small curve. You've got a small rate of change in your unit tangent vector. There's not much difference between the unit tangent vector at this point and the unit tangent vector at that point. But if you go into some place where there's a really sharp corner, you're going to have a really large curvature because your unit tangent vector is changing a lot in there. You're making a lot of change in the direction that you're going. So you're going to have a large curvature in the sharp corner part of it. You're going to have a small curvature where it's relatively flat, where it's a relatively gentle curve. Alright, let me stop this video here, and we'll look at some other ways of finding curvature, calculating curvature.